All right, this lecture at last, we will be talking about the Riemann integral. It's as the subtitle says, it's the first day of the rest of your life. So let's get going. Start off with some definitions. We begin by considering a bounded function f on a closed interval from a to b into the real numbers. We let p be a partition of this with the standard notation, partition of the closed interval ab, that is. We'll let little m sub I be the greatest lower bound of f on the ith interval, that is, the interval from xi minus 1 to xi, and define big M of I to be the least upper bound of f on that same interval. So little m is morally the smallest value, big M is morally the largest value. Okay. Since f is not necessarily continuous, there might not be points where these values are achieved within the subinterval. Let delta xi be the length of the ith subinterval. All right, let's take a look at some more definitions. We will now define the L sub p of f to be the sum of I equals 1 to n of little m sub I times delta f of x times delta of x, and u sub p of f to be the sum of I equals 1 to n of big M sub I of delta xi. All right, we'll call LP of f the lower Riemann sum of f with respect to p, and u sub p of f to be the upper Riemann sum of f with respect to p. Okay, and now we'll talk about a basic technical lemma. Let f from the closed interval ab into the real numbers be a bounded function. Let p and q be partitions of the closed interval ab, where q is a refinement of p. Then, okay, 1, LP of f is less than or equal to LQ of f. Okay, so refinements of lower sums get bigger. And UQ of f is less than or equal to UP of f, which is refinements of upper sums get smaller. Okay, we will now prove 1, okay, and we'll start by doing a very special case. We'll start where P is just the refinement consisting of the endpoints, and Q is obtained from P by adding 1 point in the interior. Okay, we can then observe that LP of f is equal to M1 B minus A, and that LQ of f is M prime 1 C minus A plus M prime 2 B minus A, where M prime 1 and M prime 2 are the greatest lower bounds of f on AC and CB respectively. Let us observe now that for that M prime 1 is, or M prime I is greater than or equal to M1 for I equal to 1 and 2. To see this, let S be a subset of the interval AB, and suppose that X is an element of S, then f of X is bigger than M1 because M1 is the greatest lower bound. Okay. Therefore, M sub 1 is a lower bound for f of x when x is an element of S. So we need only let S be AB, AC, or CB to see our observations true. So now note that we can have M1 of B minus A equal to M1 of C minus A plus M1 of B minus C. We can factor and the C's will cancel. Okay. So if I take LQ of F minus LP of F and do my algebra on it, I get M1 prime minus M1 plus M prime 2 minus M1 times B minus C is greater than or equal to 0, because all of the factors in here are greater than or equal to 0. Therefore, it follows that LQ of F is greater than LP of F, greater than or equal to LP of F. Okay, now consider the general case where Q is obtained by adding a single point C in the kth subinterval. Then subtract in the interior of the kth subinterval. Then when we subtract LP from LQ, all the terms will cancel except those from the corresponding intervals that touch the point C, and this will give us LQ of F minus LP of F equal to this expression that you see here, and this is exactly just the special case we just proved. So we're done. Now we can finally consider the general case where Q is a refinement of P and where we have a ladder of partitions where we build up from P to Q, each one adding a single point. And then we can just apply this case to all of those, and that will end the proof. Okay, the proof of 2 will follow like the proof of 1, changing what obviously needs to be changed. Now let's consider a new theorem. We have a bounded function closed from F from the closed interval A into R. If P and Q are partitions of AB, then LP of F is less than or equal to UQ of F. And this follows exactly as did a similar theorem we had when we were just talking about doing this for the function 1 over x. It follows exactly the same way. All right, now some more definitions. We now know from the previous theorem that every UQ of F is an upper bound of every LP of F, and every LP of F is a lower bound of every UQ of F. We may define U of F to be the greatest lower bound of all the UP of F, and L of F to be the least upper bound of all the LP of F, where of course P is allowed to vary over the set of all partitions of P and Q. Both are allowed to vary over all the partitions of A and B, of AB. It's clear that L of F is less than or equal to U of F. We shall refer to U of F and L of F as the upper integral of F and the lower integral of F respectively. Okay. When U of F is equal to L of F, we shall say that F is Riemann integrable on the closed interval AB, and refer to the common value as the Riemann integral of F on AB. This common value is commonly denoted by, this integral symbol. It's a stylized S from A to B of f of x dx. Okay. We'll next talk about whether such things even exist. All right. Let f from the closed interval AB into R be continuous. Then f is Riemann integrable. We will show that for every epsilon greater than 0, there is a partition P of the closed interval AB such that UF of P minus LF of, UP of F minus LP of F is less than epsilon. Okay? So start off, let epsilon greater than 0 be given. Let, for every t element of the closed interval AB, let delta sub t be greater than 0 be chosen so that when x minus t are within delta t of each other, then f of x minus f of t are within epsilon over 3 times b minus a of each other. Okay. Put u sub t equal to the open interval a minus delta to a plus delta, and let u be the set of all of these u t. Okay. By a previous result, there is a partition P of the closed interval AB such that every subinterval of P is contained in some element of u. Okay. Now, let I be between I and n. Then there is a t element of AB, the closed interval AB, such that the interval xi minus 1 to xi is contained in u sub t. Okay. So suppose that x sub I and y sub I are contained in that subinterval. Then the distance between f of x sub and f of y, f of x and f of y, will be less than 2 epsilon times 3b minus a as per this calculation. Okay, so it follows that m sub I minus big M sub I minus little m sub I will be within 2 epsilon over 3 times b minus a of each other, and therefore epsilon over b minus a of each other. Okay. All right, we can take this, okay, and go to the next slide and calculate the difference between u of f and L of f. We can so u of p, up of f minus LP of f, we can calculate just by taking the difference in the obvious way. Just roll in the definition, do our arithmetic. This mi minus little mi, we've just proven is less than epsilon over b minus a. The sum of all of the xi's are just the length of the interval, and so and the length of the interval is b minus a. Therefore, the distance between up of f and LP of f is less than epsilon. Okay. Since u of f minus L of f is less than or equal to up of f minus LP of f, is less than epsilon, and u of f minus LP of f is a fixed non-negative number, and epsilon is arbitrary, it follows that u of f actually has to be equal to L of f.